Okay, here's our function. Zeros of the numerator occur when x minus 1 equals 0. Now we could write out x minus 1 equals 0, x plus 4 equals 0. Either of these will give us a 0, but if you solve for x, you get 1 from this one, and you get negative 4 from this one. So those are the zeros of your numerator, and it doesn't hurt at that point to draw an x-axis and indicate the two zeros. Okay, now we're going to pull it all together over here with a bigger graph. Zeros of the denominator, well, x minus 2 equals 0, that's a 0 to the denominator, and that occurs at x equals 2. So draw a little axis with 2 here and a dotted line to indicate that the function is undefined on this dotted line. So you know the graph can't cross the dotted line. There's no graph point on the dotted line, right? And you also know that that's where the denominator gets tiny. And you can think about it, well, if the denominator is 2, if x is 2, the denominator is tiny. If x is close to 2, I'll say it right, yeah. If x is close to 2, the denominator is tiny, maybe positive, maybe negative, but tiny. The numerator is close to what? 2 minus 1 times 2 plus 4 is 6. So you got 6 over something tiny. You're going to get something big. I want to understand that. Okay? So, in any case, you know now that you're going to have a vertical asymptote here just by that reasoning. And the y-intercept, well, you just plug in 0, you get y equals 2, right? And you maybe draw a little set of coordinate axes with a point 0, 2 here to remind yourself. So when you do the final graph, you include that. Okay? And then the partition. Okay, the only way the function can change sign is if one of these expressions changes sign. And that can only happen if the expression goes through 0. So you look at where each of these, you look at where the numerator is 0, you look at where the denominator is 0. Those are the only places where the function could possibly change the sign. Okay, so we mark those points. And now, there's your partition. Consists of the interval to the left here, the interval from here to here, from here to here, and from here on. Everywhere inside of those intervals, each of those intervals, the function has to always be positive or always be negative. You can't change sign within the interval. So what's the sign? Well, to the left of negative 4, you have really big negative numbers. Really big negative numbers would make each of these negative. So you'd have a negative times a negative divided by a negative, which means you're negative on this interval. On this interval, you could pick any number, like for example, zeros in this interval. Since you've already calculated this function for 0, you know it's positive, right? You know it's 2. Okay? And you can also reason out that this will be negative, this will be positive, this will be negative everywhere on this interval because you just tested for 0. 0 minus 1 is negative, 0 plus 4, 0 minus 2 is negative, right? So negative, positive, negative. Between 1 and 2, well, if x was 1.5, this would be positive, this would be positive, but this would still be negative, right? So we would have a positive and a positive over a negative. Now, negative, positive, negative gives us a positive. The graph's got to be positive here. Graph's positive, positive divided by negative. Which is negative. on this interval. And to the right here, you have humongous positive numbers, makes everything positive. We've got to have positive, positive, and positive, which is positive. Okay, end behavior. Well, if x is really big, then what do you have? You have a really big number times a nearly equal really big number times a nearly equal really big number, right? Like if x is a trillion minus 1, a trillion plus 4, a trillion minus 2 minus 1, just be trillion, and a trillion, and a trillion, right? Okay? If you multiply a huge number by itself and then divide by itself, you just end up with a huge number, right? Okay? Okay? I'm going to just say it like that. Huge times a huge over huge equals a huge. Okay? Doesn't equal a humongous. Just plain old huge. Now, if it's huge here and huge there, it's at about a 45-degree angle out there somewhere, right? The point huge, huge is about there. Okay? So we draw the graph. Okay, 45-degree angle, we're going to kind of approach this here and kind of approach this. I didn't leave myself a lot of room to the left. So I'll be a little sloppy with this, but it's got to be negative here, positive in this interval, negative in this interval, positive in this interval, and it has to go through the point 0, 2. So we're going to start from way down here someplace. We're going to come up through 4. And at some point we'll turn around here, so we'll come down here and approach this negative asymptote. Okay? And then on this side, we're going to have an asymptote with this line. So the graph's going to come down like this, but then it's probably going to turn around and go off like so. There are plenty of examples in your text. But those are the ideas, and that's the kind of analysis we need to do with rational functions.